All right, so here's a few more problems for finding, critical values, absolute max and min from section 4.1. Let's say we have f of x equals x minus 3 over x squared minus 3x plus 9. And then we just want the critical values, okay? CV stands for critical values. Where do critical values come from? It comes from the derivative, right? When you set the derivative to 0 and you solve for x. Whatever makes that 0 or undefined, those are the critical values. So let's figure that out right here. Well, how do we find the derivative of a quotient? Gotta do the chain rule, right? So f prime of x right here. Remember, for the quotient rule, it's gf prime minus fg prime over g squared. So we have g times f prime, the derivative of the top is just 1, minus f times g prime. G prime in this case would be 2x minus 3, all divided by the denominator squared. Okay. And when we're setting this to 0. But let's first, clean it up. We get x squared minus 3x plus 9. Right here, we're just multiplying the 1 in. Right here, we can FOIL, right? FOIL these things, these products here, and distribute the negative. But I'm going to cover up the negative first. So x times 2x is 2x squared times the negative is negative 2x squared. And then x times negative 3 is negative 3x times another negative is a positive 3x. And then we do our inner, right? Negative 3 times a positive 2x is a negative 6x. But with the negative right here, we get a positive 6x. And then negative 3 times negative 3 is positive 9. Times that negative gives you negative 9. All divided by our denominator squared. Put the squared right there as well. And that's equal to 0. So if we notice, we can do a couple things, right? Like these 9s go away. And then we have a negative 3x and a positive 3x. That disappears. So ultimately up top, if we combine like terms, what do we have? We have x squared minus 2x squared. That's negative x squared. And then plus 6x. And the denominator is still x squared minus 3x plus 9 squared. And we're setting this to 0, right? Because again, when you set the derivative to 0 and you solve for x, that gives you the critical values. Now, what do we do with the fractions? How do we do that, right? Well, when you have a fraction, right, a rational equation, and you're setting it to 0, you have to set both the numerator and denominator to 0, okay? The values that you find from the numerator that make it 0, those are values that exist, right? Because it's okay to have 0 up top. But the values that we find in the denominator, those will cause your expression to be undefined, right? Because what's anything divided by 0? It's undefined. That would still count as a critical value in this instance. Because remember, critical values are either something that makes the expression 0 or undefined. Remember, values that make the denominator 0 will cause the function or expression to be undefined. Values that make the numerator 0 are just, that's okay, right? Because 0 divided by something other than 0 is 0. Those exist right there. So let's do that. Set the top to 0. Also set the bottom. So you may be wondering, what do we do with the squared right here? Well, you just ignore it, okay? Even if this was to the 10th power, who cares? All this means is that this occurs twice, right? So if you solve this and you get, an x value, it just means that that x value would occur twice because of the squared. Or if this was raised to the 52nd power, you're not going to write it out 52 times and solve it 52 times, right? You only need to solve this once. And then whatever power that is, that tells you how many of that specific or unique answer you have. So we're just going to say x squared minus 3x plus 9 equals 0. So with this one, what can you do? Can you factor it? Not like, the traditional trinomial way, but there's a GCF, right? We can take out a negative x, Or you can take out a positive x. It really doesn't matter. You'll get the same answer. But if we do that, if we take out a negative x, you're left with x minus 6 equals 0. Remember, we can check that, right? Negative x times x is negative x squared. Negative x times negative 6 is positive 6x. Watch the signs. So now we could say negative x equals 0 and x minus 6 equals 0. This says, oh, x is equal to 0. Right here, x equals positive 6. So these are two critical values right here. Again, what that means is if I substitute 0 into the original function or 6 into the original function, you're going to wind up with 0 up top and some non-zero term on the bottom. But remember, 0 divided by anything except 0 on the bottom is 0. So these two are definitely critical values. The ones that pop out of here, if something does pop out, these would cause your function to be undefined, right? Because if I plug 0 into the denominator and you type in, 5 divided by 0 in your calculator, you get undefined, right? So these are still critical values. All right, we need to solve for it. Let's see if something pops out. Now you may try to factor this. You may think, oh, what times what gives me a 9? And if I add or subtract it, gives me a negative 3. Well, nothing, right? Nothing nice. You can't go x minus 3, x minus 3 or anything like that, or x plus 3, whatever. It's not, you can't factor it. Remember, if you can't factor something, but you need to find solutions, what can you use? The quadratic equation, this thing right here. Y'all should remember this. You've done it or used it 50 million times. Here's the 50 million in first time. Negative b plus or minus square root of b squared minus 4ac over 2a, right? The a just stands for the coefficient in front of the x squared. Remember, this is the standard form of a quadratic, ax squared plus bx plus c right here. So we're just going to throw all these numbers in to this equation and solve it. So x equals negative b, watch the signs, plus or minus the square root of, I'm going to run out of space. X equals negative 3 plus or minus the square root of b squared, that's negative 3 squared, minus 4 times a, which is 1, c is positive 9, all divided by 2 times 1. Again, watch the signs. B was negative, so you got to put a negative 3 in right there. That's a negative as well, so we have to say negative 3, that quantity squared. And you just simplify it, right, as much as you can. You get 3 plus or minus square root of 9 minus 36 divided by 2. And then we get 3 plus or minus the square root of, what is that, negative 27 over 2. If we continue to work this out, you get 3 plus or minus 3i root 2 over 2. Remember, I could say this is just negative 9 times 3. Square root of negative 9 is 3i, right? Remember, square roots of negatives are imaginary numbers. So what does that mean? It means that if we could plug this into the original expression, we would get 0 in the denominator, which makes it undefined, which would count as a critical value. But the problem is we can't plug this in to the original function. It's kind of like saying, I want to say it's kind of worthless in this sense, because why? It's because you have imaginary numbers. Remember, these critical values, they have to be real numbers, like fractions, decimals, square roots of positive numbers, stuff like that. But once you get imaginary numbers as a result, these don't count for anything, because again, it's only the real numbers that we're worried about. Imaginary numbers don't fall under the real number family. They're in a completely other set of numbers, okay? So if you get an imaginary number, or if you get imaginary solutions can't count as critical values, okay? So basically, we would ignore these two right here. But let's say we got, like, x equals 5 in the end when we worked this out. Then, yeah, you would use that 5 and say that's one of the critical values. So your answer, or final answer, is what we initially had, which was x equals 0 and 6. Those are our critical values right here. All right. You're basically listing the ones that exist. Okay. And remember, on Webastein, I believe there already is an x equals box. So don't put, x equals and then x equals 0 comma 6, because remember, the answer box already has this. You don't need to type in x equals. If you do, it's going to mark it wrong. So you just put 0, 6. Okay. This specific question wasn't asking for the absolute max or min. Okay. So again, you have to read the directions. Don't sit there and look and say, where I'm plugging these numbers back in, but I don't know where to put the answer. But the thing is, you didn't have to plug in these numbers, okay? When it asks for the absolute max and min, that's where you plug these numbers back into the original equation along with your domain that they gave you to see which ones gave you the highest y value and which ones gave you the lowest y value. But really important with the critical values, if you have a fraction, when you take the derivative, you set the top to 0 and the bottom to 0. The ones in the top, that's fine if you get, real numbers, or we want real numbers every single time, okay? But when you set that denominator to 0, if you get imaginary numbers as part of the solution, you cannot use those as critical values, okay? So you would just ignore them. But like I said before, if we got a real number when we work this out, you got like x equals 9 or something, or 9 and -8, for example, then yes, you would throw that into this as part of the final answer as well. Now, what about something like this? Like y equals t to the 3/4 minus 6t, or I'll say x. X to the 3/4 minus 6x to the 1/4. And again, we just want the critical values, okay? Want CVs, critical values. What do you have to do? Take the derivative, right? These are fractional exponents, but still works the same way, right? You do the power rule. This is 3/4 x to the -1/4. Remember, you're going this exponent minus 1. 3/4 minus 1 is -1/4. This is minus 6/4 x to the -3/4. Okay. You may be wondering, do we reduce this right here? You could, right? Because this is 3/2, but I'm leaving it in this form for a specific reason. And the reason is because we're setting this to 0. If we solve this for x, what we want to try to do is factor it, right? It's not a trinomial, but there is a GCF. We can actually pull out a 1/4. We can actually pull out a 3/4 x to the -1/4. Okay. So what happens, right? I know it looks kind of crazy, but if I pull out, remember, as far as the exponents, it's the one with the lowest power, right? So the 1/4 is smaller than the 3/4. That's why we took that out. As far as the numbers, well, they both had fourths. You see, that was the reason why I left the denominator as a 4 right here, and I didn't reduce it to 3/2, because it's kind of harder to see the LCD between 3/4 and 3/2, right? Right here we can see, oh, it's just the 3/4. So if I factor out a 3/4 x to the -1/4 from itself, remember, factoring out just means dividing it. If I divide this by itself, we're left with 1, right? Remember, we can check that. How? 3/4 x to the -1/4 times 1 gets us back to here. So we did that correctly. What about the next piece? Well, so I'm dividing a 6 by a 3. What's left over? A 2. What about the 4s? If I divide a 4 by a 4 out, what am I left with? 1. So that you're just left with a 2. What about x to the -3/4? And we factor out an x to the -1/4. Remember, when factoring out means dividing out. So you'd be left with a -2/4. And of course, yes, we will reduce that. I just left it like this. Where did it come from, right? Because remember, when you're dividing bases, what do you do with the exponents? You subtract. So we really have -3/4 minus a -1/4. So that becomes positive, and you get -2/4. Of course, you could always check it, right? What happens if I multiplied 3/4 x to the negative 1/4 times 2x to the negative 2/4? What happens right there? Well, 3/4 times negative 2 is negative 6/4. X to the negative 1/4 times x to the negative 2/4 gets you back to x to the negative 3/4. Because remember, when you multiply similar bases, what do you do with the exponents? You add them. Negative 1/4 plus the negative 2/4 gets you to x to the negative 3/4. And all this is set to 0. Okay? So now we have 3/4 x to the negative 1/4 equals 0. We also have 1 minus 2x. And I'm going to reduce this negative 2/4, okay? I'm going to reduce it now to negative 1/2. Right? This just becomes negative 1/2 when we reduce it, equals 0. Now we need to solve these, right? Because we've got to solve for 0. Well, if you have negative exponents and you need to solve for 0, make the exponents positive. How do we do that? We flip it, right? So we say, oh, this is 3/4 x to the 1/4 equals 0. Remember, you only flip the x because it's the only thing that has the negative being applied to it. Same issue right here. This is 1 minus 2 over x to the 1/2 equals 0. You only flip the thing that has the negative exponent being applied to it. So with this, how do we work this out? Well, it's a fraction, right? Remember, you set the numerator to 0 and the denominator to 0 if they had x's involved. But saying right here 3 equals 0, that doesn't really tell me anything. There's no x to solve for, right? So you can just ignore that right there. But the bottom has an x in it, right? So we have 4x to the 1/4 equals 0. So then, you divide by 4 and you get x to the 1/4 equals 0. What does x have to be right here? 0, right? That's a critical value. But in this instance right here, this would make the derivative undefined, right? So if it makes it undefined, that counts as a critical value. So critical value, since it makes derivative undefined. Now remember in the last problem when we had to do the quotient rule and we set the denominator to 0 and we got that I stuff. Remember, we didn't include that answer. Why? Because critical values can only be real numbers. 0 is a real number, right? That's why this will be part of the answer, okay? Imaginaries aren't in the real number family, so we cannot include those. Now we need to solve this one, right? Got to solve this one right here. How do we do that? All right, so right here, I can just add this 2 over x to the 1/2 to the other side. I need to get that x to the 1/2 out of the denominator, and I want it to stay positive. Yes, you could flip it back up, but that'll make it a negative exponent. We don't want that. So I'm going to multiply both sides by x to the 1/2. So now we have x to the 1/2 equals 2. This x now is in the numerator, okay? This is going to count as just a regular old critical value. It's not going to make it undefined, okay? Because again, this x is in the numerator. This one made it undefined because where was that x? It was in the denominator. This one's in the numerator. Now we have x to the 1/2 equals 2. How do we get rid of the 1/2? Well, what's the opposite of raising something to the half power? It's squaring it, right? Square both sides. Because what's x to the 1/2 squared? It's just x. Remember, power raised to power, you multiply. So 2 times a half is x to the first, or it's 1. And what's 2 squared? 4. So there is your other critical value. So final answer is x equals 0 and 4. So this, remember, we use that 0, even though it makes the derivative undefined because 0 is a real number. If we work this particular x portion out with the x in the bottom, and we got an imaginary solution, you would not include it as a critical value. But because we got a real number, yes, we can use it, or we need to list it. This one right here, we also got a real number, so we need to list it. And then you stop right here. Again, don't type in x equals on WebAssign. It already has the x equals there. You just put 0, 4, for instance, and that would be the correct answer. Let's see, any other ones? Oh, that should be it.